Hello everyone, my name is Krishna. Today I'm going to explain about a new research published about LLM, which is enhancing character level understanding in LLM through token internal structure. Let's dive right in. So, these are the authors of my research paper, and it is published at rziv.org on 26th November 2024. So, why choosing this paper? So this paper basically finds to establish a relation between words and their position using tokenization techniques like byte pair encoding or byte level byte pair encoding. So this affects vocabulary representation and stability of the LLMs, especially when they are fine-tuned to a specific task. Hence, they discovered a new technique called tipa, which is token internal positional awareness. So this is used to train LLM after converting them into tokens by studying the intrinsic characters of the internal tokens. So this technique not only improved stability but also improved model convergence when they downstream this LLM to a specific task. This specific task can be anything like text generation, machine translation, etc. So what is our problem statement? The statement is to actually identify the complex word structures in high-level languages or multiple languages or out of vocabulary words in multi-languages. So why does it matter? The basic necessity for natural language processing is it performs certain tasks such as spelling correction, named entity recognition, and also key phrase entity in the sentences, and machine translation, text generation, and sentiment analysis, and many other. So the whole world revolves around LLM and NLP for real life implications. So current models like GPT, BERT, they rely on tokenization. So when this problem is not addressed, it could limit the potentialness of these LLMs by leaving out most important semantic word understanding. So in multiple languages, causing bias in the output, so that your output would be kind of off giving and not accurate. So the previous approaches before this technique was researched were usually uh, byte level encoding, subword tokenization. So tokenizing the word into multiple times, that is called subword tokenization, and it showed no improvement because it could not capture the internal character position. So the words or the characters in a position were not captured efficiently, so that it affected the complexity, and also it did not provide a huge performance. So what is the solution? They came up with a technique called TIPA, token internal position awareness. So it is introduced to teach LLMs about the importance of positions of characters within the internal tokens. So what are the innovations? The words are converted into set of tokens. After training the model, the words are converted into tokens which are vectors, which has start and end token to define the length of the word, and also a sentence, and train the model from start token to end token. So this basically is known as attention, and self-attention is what the transformers architecture or any other BERT or GPT models actually use. It could be an encoding or decoding or total transformers architecture. So instead of starting or training a character from start to end position, what if we could reverse it? What if we can train the characters from end position to the start position? Now that's what exactly this innovation does. This technique does. So we started from the end token and trained all the words from ending to beginning to extract the intricate patterns and understand the position importance of each character in the specific word. So this actually improved the LLM vocabulary, and also we developed something similar to multi-attention, which is called multi-token internal position awareness. So you train or you uh, tokenize the words parallelly at the same time using a position mapping D, which is a weighted matrix. And this matrix tracks all the characters from the ending to the beginning. So we extend this to the full sentence at the same time so that we can understand the broader context of the sentence. So, what are the main contributions in this research? It actually improved the character level representation across multiple languages by understanding better token structures, and it also improved significant performance in Chinese spelling correction language tasks. Yes, this is specifically researched on a Chinese language or considering Chinese texts or Chinese sentences. And it also showed faster convergence and high accuracy in many NLP character sensitive tasks, such as spelling correction, named entity recognition, and also machine translation. Okay, so now compared to the results, so it exactly showed 15% more accuracy compared to baseline LLMs, and it also enhanced generalization in low level languages. Low level resource in meaning the languages which do not have too many words. Now English is considered as a complex language because it has too many words, but some languages like Chinese traditional, which do not have too many words, and they are considered as low resource languages. So TIFA, or our technique, with a 7 billion parameter, outperformed SFT. SFT is nothing but baseline LLM. So that's a normal fine-tuned LLM, but it's a normal LLM without using our technique. So what are the limitations of this model? Again, the limitations are this model is only explored for Chinese language. So it is not explored for other languages such as Japanese and Korean. So the method for predicting out of vocabulary words which do not directly appear in the tokenizers vocabulary, they need to be further researched because the accuracy is not good enough for out of vocabulary words. And the potential applications where this can be used for spell checker websites, like you can implement for spell checker AI to give you a better fluency of the language, and it also can be used to translate from one language to another, such as machine translation. And the future work can be improved to target a specific industry by developing a lighter version which is more flexible and can be faster and can be inferred faster. And we can also explore multiple model application tasks by using this method. And the strength, as I said, it handles character level information, especially as it showed 15% more accuracy than the baseline models. And it also understood internal position of the characters and the importance of positioning a particular word in between the words, in sorry, particular character in between the words. And weakness, as we are dealing with the internal layer, so basically inside the word for every character, it is highly computational and it requires highly specified fine tuning. The reason, if it is not fine tuned well, again, it could provide inaccurate output. So the text generalization may have a lot of grammar mistakes. So for fine tuning, it needs to be trained a lot. So this is a lot of research amount or research extensive. So, and also fine tuning takes a time and also takes up computation as well. So the insights, what are the insights we got from this? The approach shows that we haven't fully understand LLMs. There is so much we need to learn, but it also showed a promising development in the LLM. So it is not like halted in the LLM research area. We are still able to undiscover, or we are still able to discover many new things. For example, we now discovered some development in low resource level language, but also for it to deploy in the real life implications, it needs to be more researched and studied. So the conclusion is, so we have created an innovative approach for improving the LLM character level comprehension, demonstrating notable gains in spelling correction and other NLP tasks. And this is the link to my research paper. So this is basically how they used TIPA, TIPA to actually improve LLM understanding of the words, helping to attention process in the transformers architecture. And this can actually prove more worthy because chat generation is the next big thing that people are using. And thank you.